All right, you're welcome. All those people online. All right, hold on, please. Okay, I just want to put my okay. All right, so who is online? You're welcome. Who is online? Please indicate. Let's proceed. How are you? How was today? So I'm looking at energy quantization. That's the topic for today. Okay. Energy quantization. Where is Onyema? Where is she? They should log in. Maruchi and Co. Celebrity. Where are they? They should log in. Let's start. While I wait for them, let me just write a brief introduction of this topic so that we can start. All right, that is Lisa. You're welcome. Okay, you're welcome. How was today? All right, so energy quantization, I'm going to briefly explain it, okay? I might even do a small write-up because you need to put something down. All right, before we go into the calculation part of it. Atoms in electrons, so let me say atoms occupy certain energy levels, okay? Atoms occupy certain energy levels. And when they are heated, they tend to do what? They tend to vibrate and move from their original ground state to a higher energy level due to what? The excitation or the heating that they acquired. But because the excited state, they are not stable, after a while they're going to return back to their normal state. And as they return back to their normal state, they're going to emit an energy called what? Photon. And that is what we may be asked to calculate under this topic called energy quantization. So that energy that atoms emit is said to be a photon or quanta. Okay, it's a quantum of light that has a characteristic frequency or may be asked to calculate as the energy released. So I'm going to write some things down so that you can use it to understand the concept. Okay, so let me put it down. I'll wait for the rest to join the class. Okay, so we are all right. Okay, let's proceed. I'll say atomic energy level. Okay, it's just a brief write-up. Electrons in atoms. They are believed to be arranged in positions known as energy levels. Okay, then I'll just be fast. Electrons in the orbit closest to the nucleus have the highest energy levels. Okay, so let's just be fast. When an atom is heated, okay, or bombarded with an energetic particle, okay, its temperature is increased, its energy is increased rather, is increased, and the atom is excited. All right. The atom tends to jump to a higher energy level, okay? And also returns back to its original energy level to emit an energy or quantum of light. I just summarized everything because this is the reason I'm going to write on this. I just summarized it so that we can do other things, okay? All right, I just summarized the long story, I just summarized it. So I'll just be able to explain it with a diagram and we'll just forge ahead because of time. All right, so let me just be explaining why you've copied. Okay, let me just read it out. Electrons in atoms are believed to be arranged around their nuclei in positions known as energy levels. Okay, if you have your new school physics with you, later you can go through all those write-up. I just have to summarize because of time. Electrons in the orbit closest to the nucleus have the highest energy level. Now, electrons in their orbit are said to be in the ground state, okay? I didn't include that one. All right, so when an atom is heated or bombarded with an energetic particle, its energy is what? Increased. And once its energy is increased, the atom is said to be excited, okay? Once the atom is excited, it's going to move or jump to a higher energy level. Then after a while, because excited states, they are not stable, they tend to return back to its original energy level. In the process of returning back to your energy level, they're going to emit an energy or quantum of light, okay, which has a characteristic frequency, and that is what you may be asked to calculate. Is it okay now? The camera, I think, is okay. All right, so that is that. Please, if you are just joining, this is Jossy Science Academy, please subscribe to this channel and give it a thumbs up, okay? Subscribe to this channel, give it a thumbs up for JAMB 2026. All right, so that is that. If you are done with the write-up, please let me know. If you are done with the write-up, let me know. So let me just explain it further with a diagram. So you can go through your physics textbook under this topic and run through all those explanations there. I was going to summarize it with a diagram because of time. Celebrity, how was today? All right, Lisa, you are done. Okay, please, who else is done? Let's proceed. Name, are you done? All right. Celebrity done. I want to clean the board. All right. So look at energy transition. All right, this is what we call energy transition. Okay, so E4. All right, so this is E3 minus E0. This is E2 minus E0. This is E5 minus E2. This is E4, E1. All right, so let me explain. I was saying earlier that atoms that is in their normal state is said to be in their ground state, okay? But if they are being bombarded with an energetic particle, they are going to move or jump from one energy level to another. Now, this atom jumped from the ground state to energy level 3. Why did it jump? Because it was excited, right? But because the excited states are not stable, it jumped from is not that is the ground state to what? Energy level 3, right? Now, because this energy level 3 is not what? A stable state, right? Because it is not stable. So it's going to return back to its normal state. Okay? As it's returning back to its normal state, it's going to emit an energy or quantum with this formula. So it came back from energy level 3 to energy level 0, right? This one came from what? Energy level 2 to energy level 0, right? This one is what? Energy level 5 to energy level 2. So that is what we mean by jumping and bombardment. Once an atom is being bombarded, it tends to move or jump from its original ground state to another higher energy level, right? To return back to its normal state. Reason is because the excited states are not what? Stable. They can't remain there for a long time. They're going to return back because they jumped to the higher energy level because they were excited by bombardment. Okay, so after a while they return back to its normal state and they're going to emit energy in form of a photon as they're returning back because it was a higher energy that took them there. So as they're coming back, they're going to emit that energy. Do you understand? So that is what we mean. So now the energy that they emitted is from different energy levels, from the higher energy level to a lower energy level, right? So we have this change in energy as the electron jump from a higher to a lower energy level. Now it's equals to HF. Okay, now this is the frequency of the emitted photon, and it's a constant, which is what's called Planck constant. Do you understand? So this is the energy of the emitted photon. This is the energy of the emitted photon. As this atom is jumping from a high energy level to the lower one, which is their original ground state, they're going to emit what? A quantum of light, which has a characteristic frequency with this relationship. This is how they wrote it in your textbook. A quantum of light that has a characteristic frequency of this relationship, right? So the change in energy is equal to HF. What is this delta E? That is the change in energy levels, right? That is from one energy level to what? Another. What is H? Planck constant. What is F? Frequency. All right. So we have that. This is what? Energy of emitted photon. Okay. H is Planck constant. Okay, F is frequency. All right, remember that from the speed of light, because electrons can move with the speed of light. Okay, from the speed of light, C is equal to F what? Lambda. If we decide to make F the subject, F is equal to C over lambda, right? So we can put this in this equation to have that the energy of the emitted photon is equal to HF or is equal to HC over lambda. So this is very, very important. Are we cleared? All right, so you can put it down. Let's proceed. Please, do you have any question with the explanation? Do you have question with the explanation? I said atoms tends to be excited if they are being bombarded, right? And once they are excited, they tend to jump from a lower energy level to a higher one, which is the excited state. But because that is not their original state, look at it. This first one jumped from energy level 0 to energy level 3, right? But because energy level 3 is not its own original state, so it has to return back to its what? Its normal state. That is from energy level 0 to 3 to energy level 0. Now, as it's returning back, it's going to emit an energy, which is a quantum of light with a characteristic frequency of what? Delta E is equal to be using to calculate the change in energy, the wavelength of the emitted photon, the frequency of the emitted photon, right? So you still remember that the speed of light, C, is equals to F lambda, right? So making F the subject, We now have that F is equal to C over lambda. Is that cleared? Are we cleared? Okay, please put it down. Are we done, please? Are we done? Do you have question? Do you have question? Please, class, are we done? Do you have question? All right. Please also be checking on my channel by every 8 p.m. I'll be posting videos on different topics, most repeated questions on different topics. 8 p.m. on the questions that I'll be dropping every day, right? It will also help you. That's a form of revision for you. Helen, you're just coming. You can screenshot. You can screenshot it, okay? Celebrity. You don't understand? Okay, let me explain it again. Because of time, I do not want to do, okay? So, celebrity. Let me explain, okay? I said that atoms in their original state, this is the original state of this particular atom, right? So, but during incitement or during bombardment, okay, they tend to jump. When they jump from a lower energy level to a higher energy level. This one jump from energy level 0 to energy level what? 3, okay? While this one jump from energy level 0 to energy level 2. They keep jumping. But most important is this. It was coming from a higher energy level, right? So now, because this is an excited state, okay? So excited state, they are not stable. Because they are not stable, they're going to return back to this normal state. As they're coming back to the normal state, they're going to emit a photon of energy or quantum of light and emit it in this change in energy, right? E3 minus what? E0. That's the change in energy with a characteristic frequency with this formula. So the energy of the emitted photon, E, is equal to HF. Okay? What is H? Planck constant. What is F? Frequency. Do you understand? So electrons keep jumping from one energy level to another in as much as they are what? They are being excited or being bombarded. Jumping from one energy level to another. But after a while, because this excited state, they are not what? They are not stable. So it has to return back to its normal state. As it's returning back, it's going to emit an energy with that formula on the board. So this is what we're going to be using to solve problems. And I said that the speed of light C is equal to F lambda, right? Making F the subject, we have C over lambda. So if a question does not even have frequency, but it has speed of light and wavelength, we now use this one to solve your problem. Is that clear? Are we clear? Are we clear? All right, I'm done explaining, okay? So now this is a 1 hour class. Let's see how we can utilize it very well. Let me solve 1 or 2 problems you're going to understand better. Okay, so let's proceed. All right. Okay, so let's go. Please give this video, give this class a thumbs up. I'm seeing just 5 likes. Is it that people don't like the topic? Please give it a thumbs up. Oh. All right, so let's start with example 1. Let's start with example 1. Question 1, I will say an electron. An electron makes a transition from a certain energy level, EK, to the ground. Ground state, EK 0. Of emission, is 8.0 times 10 power 14 Hz, right? The energy emitted is what? You have the following options. Option A, we have 8.25 times 10 power minus 19 joules, right? We have 5.28 times, we have 5.28 times 10 power minus 19 joules. We have 8.25 times 10 power minus 19 joules. Okay, so this is just 19 joules, right? So in the question, we're given Planck constant H to be 6.6 times 10 power minus 34 joules second, right? Okay, class, look at this question. All right, you said why did E5 not return to E0? Okay, so it must not return to E0. It depends on its original ground state, right? So you just have to answer the question the way it is. It must not return to E0. It depends on the ground state. Do you understand? The ground state for that E5 was not E0. So it can jump from any level to a higher energy level and return back to its original energy level. Do you understand? Okay. Oh, okay. Minus 19, minus 19. Okay. So this one does not have minus, please. Okay, I hope that is clear. Thank you so much for that observation. My wellness, ma, tomorrow by, I think our class will be 6 p.m. because I'm teaching day students, so I need to be able to finish and have time to read before I do our own. So let's be keeping our class to be 6 p.m. please. I think it's better for me. All right, please, let's solve this question. An electron makes a transition from a certain energy level, EK, to the ground state, E0. Are you listening? All right, if the frequency of emission is 8.0 times 10 raised to the power of 14 Hz, the energy emitted is what? And we have Planck constant given. And we have the following options. I think this particular question is self-explanatory. Look at it. It makes a certain transition from EK to the ground state. So that means it jumped from EK to its ground state. Okay, and it gave us the frequency as that value. We are looking at, yes, we are looking at the emission, the energy of the emitted photon. Remember, okay, let me just say the parameters. We are given the frequency F to be 8 times 10 to the power of what? 14 Hz, right? Now we are given the Planck's constant H to be 6.6 times 10 to the power of what? Minus 34 joules second. Are you clear? Now we're looking at the energy of the emitted photon. Then this energy of the emitted photon, remember, is equals to HF. Okay? Remember. So just multiply these two values, voila, and we are done. So this is 6.6 times 10 power minus 34, then times 8 power minus 14. Are we clear? Now we can solve it out and get our answer. Who will solve it for us? Or someone will be like, how can we solve this without calculator? We can actually do that. You can make this thing to be a whole number, right? By saying that this is 66 times 10 to the power minus 1 times 10 power minus 34 times 8 times 10 power 14. Do you understand now? We can now multiply 66 by what? 8. And then work on the powers. Is it possible? Sochima, is that you? Option B, I have an answer. So who else is solving? What do you have, please? You see what I just did? You may be like, how can we solve this particular question without calculator? So that's 6.6. You can change it to be 66 times 10 raised to the power of minus 1. Okay? All right. So that way you can now multiply 66 by 8 to get your answer. Then work on the powers. Are we cleared? So who is solving? Already have option B. Okay, you're welcome. All right. So who else is solving? Do you have an answer? Work on that and tell me what you have. Option B, okay. Do we agree with that? The rest, do we agree with option B? Did we solve it? All right, option B. All right, so the rest, okay. Lisa, you got what? Option B. All right, so that is the answer, right? Okay, so the answer to this question is 5.28 times 10 to the power of what? Minus 19 joules. That is my change in energy. Okay, so option B is the correct answer. All right. All right, so can we go to the next one? Any question? Any question? Let's go to the next question. Next question. Next question. All right. So, next question. Question 2. All right, the question says, the ground state energy for a hydrogen atom is 5.44 times 10 power minus 19 joules. If an electron drops from 0 energy to ground state, calculate the frequency of the emitted radiation. All right, so we have 6.6 times 10 power what? Minus 34 joules second. Okay, so let's look at the options provided. First option is this. Okay, so this is a 2.0 times 10 over 15. We will have 5.0 times 10 power 16 here. Then I have 5.0 times 10 power 16 here. Oh. One should be plus, one should be minus. Okay, hold on. Okay, but I saw the same value anyway. Maybe it could be a mistake from Planck constant. You know that the energy of the photon is proportional to the frequency of the emitted photon. All right, so when you remove that proportionality and introduce a constant, which is the Planck constant, so that is what we are using to solve problem, and it's always a constant. Okay, so class, look at this question. The ground state energy for a hydrogen atom is 5.44 raised to the power of minus 19 joules. If an electron drops from 0 energy to the ground state, calculate the frequency of the emitted radiation. Okay, so we are given H, which is the Planck constant, as 6.6 times 10 raised to the power of minus 34 joules second. Now, what are we looking for? The frequency. This one too is quite simple. We have that the change in energy is equal to Hf, right? What are we looking for? The frequency of the emitted photon, right? Now we have the energy to be this. I'll say this is the change in energy is given as 5.44 times 10 power minus 19 joules. The Planck constant is given as 6.6 times 10 power minus 34 joules second. We are looking for what? F. Is it clear? This one is still quite simple. You can just work on it, divide both sides by the frequency, by H rather, to get your frequency. Okay, now if you do that, you are going to have that the change, that frequency is equal to change in energy over H. Okay, now we have this, which is 5.44 times 10 power minus 19 divided by 6.6 times 10 power minus 34. Okay, now you can work on that to get our frequency. Is it clear? Do you have question? Chidera, do you have question? This one is self-explanatory. Do you have question? Do you have questions? Go ahead and ask your question if you have. Any question? All right, so can I see your question? Please send in your question. Yes, please. I'm waiting for your question. If you are done, let me know. Let's move to the next one because of our time is running fast. Work function. I've not gotten to work function. That will be tomorrow. They are related, but not exactly. Okay? All right. That is under photoelectric effect. Okay? I'll do that tomorrow. So today I'm just talking about energy of the emitted photon. That will lead us to work function. That will be tomorrow. Is that okay? All right. All right. I think we are done, right? Let's move to the next question. Let me see if we can actually solve this one. All right. I'm having different answer. Which answer do you have? Nobody has even given me answer. Please, what's the answer in this one, Seth? Before I leave it. What's the answer, please? What did you get? Divide that stuff on the board. 5.44 raised to the power of minus 19 divided by 6.6 times 10 to the power of minus 34. Please, what's your answer? Please, what's your answer, please? What's your answer, please? I'm waiting. Do you have an answer? .24 times 10 to the power of minus 14. I don't have that in my options. Okay. I don't have that in my options. So try again. Check where you made a mistake. Sochima. Okay, I don't have such in my options. Please, who else is solving? Onyema, what's your answer? Lisa, what's your answer? Bonaya. Celebrity, what's your answer, please? Please, what's your answer? Somebody's having a different answer here. Please, what's your answer, please? What you also got? Okay, let me find out why. Oh, well, um, okay, the thing is that it's from what I saw from the past question. Probably they made a mistake. Okay, so maybe they made a mistake in their what they typed. I just copied it from there. 2010, number 47. Yes, I just solved it now, and I realized maybe the answer is not here. I think it's from people that typed it. So I got the question from 2010. I'm using prep 50 actually, okay? I got 2010, number 47. Okay, maybe if you have a past question, or you can check online actually for 2010 JAMB question, physics, number 47. You see the question, confirm the answers, okay, the options. But this is what I saw from prep 50. If you're using prep 50, you can confirm that with me. I think that is an error. So please disregard this. This is not correct. Okay? This is not correct. I think they made a mistake. They made a mistake, okay? They made a mistake. Celebrity. Yes. My answer gave me 8.2 something. Let me do it again. .24. Do you understand? 8.2 raised to the power of. I've not worked on the power yet, so that was when I realized that the answer is not here. Okay, so please check from the what I wrote. I got the question from 2010, question 47. Okay, please check. I'm using prep 50 and I just copied what I saw there. This should be an error. Okay, so the answer is 8.24 times 10 to the power of what? 14, I think so. Please confirm from the question. The options, they are not correct. All right. So I think we are good to go. Let's go to the next one. Question 3. All right. Question 3 goes this way. Energy associated with the emitted photon. When the mercury atom changes from from one state to another is 3.3 electron volts, right? Calculate the frequency of the photon so I give 1 electron volt to be 1.6 times 10 power minus 19 joules, right? And we're giving H to be 6.6 times 10 power minus 34 joules second. All right. So we have the following options here. Option A, 8.0 times 10 power minus 14 Hz. Option B, 3.1 times 10 power minus 52 Hz. Option C, 1.3 times 10 power minus 15 Hz. Option D, 3.2 times 10 power minus 53 Hz. All right. So class, look at this particular question. Celebrity, that question is faulty. This the options provided, none of them is correct. So I typed it. Okay, so just solve it using the formula. Anything you get is your answer. Do you understand? Okay, so that is one of the things we see when we copy from past questions. But if you know the correct solution to a particular question, just solve it and get your answer. All right, so now look at this question on the board. The question says, the energy associated with the emitted photon with a mercury atom changes from one state to another is 3.3 electron volts, right? We are asked to calculate the frequency of the photon, and we are given electron volts to be 1.6 times 10 raised to the power of minus 19 joules. And we have the Planck constant to be 6.6 times 10 raised to the power of minus 34 joules second. Okay, now what can you say about this question? Is it similar to what we did before, or is it like different from what we did before? What do you think? What do you think? It's similar. Okay, so someone has given me answer. The only thing that is different from this one is that the energy is now given in electron volts, no longer in joules, right? So we need to multiply that electron volt with that 3.3 to make it to be in joules, right? Before we can now start solving our between this one and the previous ones we have been doing. All right, so let's go. Energy is given as 3.3 electron volts, right? But 1 electron volt is given as this guy, right? It's given as 1.6 times 10 power minus 19 joules. Okay, so by the time you multiply by this, becomes joules. You can even multiply it now by saying that E is equals to 3.3 times 3.3 times 1.6 times 10 power minus 19. So it will be in joules, right? Please multiply it and tell me the answer. Now we have the Planck constant to be 6.6 times 10 power minus 34. We're looking for F. Okay, from our formula, change in energy is equal to HF, okay? So my F is equal to change in energy over H. Are we clear? All right. So this is section as saying 3.3 times 1.6 times 10 to the power of minus 19, then divided by 6.6 times 10 to the power of what? Minus 34. Okay, look at it. No, this is JAMB for you. This can actually work on each other, right? Now, this can divide itself to give us 1, divide this to give us what? 2. Okay? Now, 2 can divide this to give us 1, divide this to give us what? 0.8, right? We can now work on the powers. Am I correct? If I am correct, so let's go. So this will give us 8 times 10 to the power of what? I'll add this to be minus 20. I'll say minus 20 times 10 to the power of what? 34, right? So that gave rise to 8 times 10 to the power of what? Minus 20 plus 34, which is 8 times 10 to the power what? 14 Hz. So most things you don't actually even need calculator to solve. You can actually do that with your brain. Okay? All right. Chukwemeka, you're late. Do we have questions? See what I just did now. See what I just did. Without using calculator, we can actually do that. All right, do we have question? Do we have question? Do we have question? With this, we can answer some questions or even most questions involving energy of the emitted photon. So tomorrow I'm going to look at photoelectric effect. Photoelectric effect. Okay? Einstein's equation. I'm going to look at Einstein's equation, the one that involves maximum kinetic energy, work function, threshold frequency, and the rest of them. That will be tomorrow. Okay? So do we have questions before we proceed? If no question, let me drop an assignment for you to solve and drop your answer in the comment section. And remember, my video will be up by 8 p.m. every day. So go and look at it. I think I did electrical energy and power. Look at it. Most likely questions, most questions that JAMB repeated some years ago on that particular topic, okay? So go there and watch the video and learn more, all right? Okay. So I think we are done. Let me drop an assignment for today. Okay, what's your question, please? Helly, what's your question? On which topic? Your question. I'm waiting. So let me write your assignment for you. I hope are we done writing? Can I send the link for 8 a.m. class? Huh. No, it's not possible. I'm working. So I work during the day and I teach some JAMB students in the afternoon. So I have to do this one by this time so I can meet up. All right, so this is your assignment. Work on it and send in your answers. Okay. It's long and has a diagram. You can send it to my WhatsApp. Send it to my WhatsApp number. Let me see. Okay. You can send to my WhatsApp number. I can, if this thing has diagram. Let me see. All right, please, this is your assignment. You can work on it. Send your answer in the comment section, okay? So meet again tomorrow by 6. p.m. Chidera, is 8 p.m. You're welcome, celebrity. It's 8 p.m. Celebrity, what of Faye? You have not seen him for a while now. When you tell your friends that my students have not yet joined, though, tell them that we have started the online classes. Okay? You're welcome. When you tell your friends that have not started, I've not seen Corazon, I've not seen Obijuru, I've not seen a whole lot of them. Okay, maybe I'll chat him up. I will chat him up personally to know why he has not been online. You don't have my WhatsApp number. This is my WhatsApp number here. This is my WhatsApp number. You can send a message on WhatsApp. Let me see. Can snap the video and send. Let me see what you have. All right. So we should call it a day, Ben. All right, so we'll continue tomorrow then. If you have questions, you can send me a message on WhatsApp. You have given me C already. I need the answer to be in the comment section, not here. So see you tomorrow, guys. All right, bye.